We have come to the end of week 2. We have looked into a lot of new concepts, and it is worthwhile to summarize the salient point of this week. First, we looked at the concept of numerical accuracy from different perspectives. The first type of error we addressed emerges from linearization of any nonlinear phenomena. The second type of error is due to spatial discretization. We also called this type of error as the staircasing error in the case of finite difference method. The third type of error comes from floating point truncation or the round-off error in our calculation. We have a similar type of error that we addressed while studying Taylor series approximation. If you remember, we talked about the order of truncation error while introducing Taylor series approximation for different finite difference schemes. In any modeling exercise, the total error is a summation of all these errors. We have looked at a graph which illustrates this as a function of spatial discretization. We also addressed another type of numerical error related to the phase of the numerical solution, which is termed as dispersion error. Later, we looked at the concept of stability of a numerical scheme. We briefly introduced the Lax theorem for stability and also investigated the role of error amplification factor. We shortly mentioned about von Neumann analysis for the stability to study the stability of any numerical scheme. We derived CFL-like condition for forward in time centered in space scheme, giving the analogy of the light cone. As a first exercise, we studied one-dimensional Helmholtz equation and calculated the eigenvalues by changing various parameters of the simulation. We also noticed the accuracy of the simulation improved as we refined the spatial discretization, which confirms that the solution is converging and the method is stable. The next exercise is that of a coaxial rectangular capacitor, where we calculated the capacitance per unit length by solving Laplace equation. We used Gauss-Seidel iteration method in order to compute the solution of the algebraic finite difference equation. We remarked that the solution converges and the speed of conversion itself greatly varies by the choice of proper iterative method. We also noticed that the accuracy of computed capacitance improved with respect to mesh refinement, confirming the convergence of the method. We noticed that the forward in time centered in space scheme is inherently unstable, and one has to keep the time stepping prohibitively small to simulate any practical problem. In order to cure this instability, we introduced the Lax method. We illustrated the Lax method using an example of advection equation. The gist of this method lies in taking the average of two neighboring spatial terms in the forward in time centered in space scheme. I encourage you to practice the exercises and examples that we have studied in this week and get ready for the next week. So until then, goodbye.